Hello everyone, welcome to the presentation. My name is Sangdae Lee. We are from Professor Joo-Hoon Bak's lab. My team member is Ji-Soo Yoon, Sungmin Jo, and Taeyeon Kim. Before I go, I want to thank Professor Bak, who has been a huge supporter for us and given us courage to finish the 10 months of research. Thank you. The presentation consists of 4 parts: frames, selecting an effector motor, and simulating controllers, pool table game simulation, and estimating ball positions. Now, let's start. We got the idea of the structure of the entertainment robot from Claw Crane, in Korean 인형뽑기. As you may have seen one, there are 2 parts, XY robot and Z roll and an effector. When we just started this project, we tried not to focus on the mechanic parts since they would take tremendous amount of time. However, after researching for XY robot in the market, we had no choice but to make it on our own because of the size and cost problem. So, to make XY robot, 2 elements: reducing the friction on the linear motion and transferring the power to the motion were needed. Considering cost effects and efficiency, we chose Allen guide as a friction reducer and timing belt and pulley as the power. As for the Z-roll, we went to the mechanic manufacturing company in person and ordered a steel bar which would roll the Z-axis. To combine parts together, combining parts should be ordered as we designed them in CAD. But in that case, to save our budget and time, we used 3D printer as robotics in Kwangwon University offers us for free, and prints the parts out such as a rectangular empty frame that is combining aluminum frames together at a right angle, and motor mount and encoder mount to fix them precisely to the Allen guide. When hitting the ball in the pool table, the speed of the ball is very important. This section is dealing with how we chose the end effector motor, which will determine the speed of the ball and what controller is better for our system. Our aim is to control the velocity of end effector motor. To do that, we had to take our first step, modeling the end effector. First, we designed a weightlessness end effector model of 15 cm with no mass. And we measured the distance of the end effector traveling and determined the last velocity just before it hit the ball, 5 meters per second maximum. The angular velocity was 33.3 radian per second on condition of the motor exerting uniformly accelerated motion. We found the motor exactly we needed, as you can see the red box on the chart. The motor company offers the parameters of the motor, and with them, we start the motor simulation with MATLAB student version for selecting proper controller. After simulating with PI controllers with anti-wind-up, we needed a fast response and came up with PIIP controller. As you can see, alpha is the coefficient of PI and IP controllers. By setting it 0.5, we reached what we desired. Now the pool table algorithm. To visualize and simulate the pool table, we used Processing, the software based on Java language, and made a virtual pool table environment with exact size of the frame and the balls, and with the approximate friction and collision event. And we put random position of the balls on the table and give a ball velocity and direction. After doing a number of times of collisions, we recognize it succeeded hitting the 2 red balls without hitting the other. Let's look at the video. When we put the mouse cursor on the 4th ball above the pool table, the code calculates what the consequence will be if the ball has a certain direction and velocity by making 72 direction events of each 0.5 degree around 360 degrees with 3 levels of speed on the center of mass point of the ball until all the balls stop. And it saves the combination of the speed levels at a certain degree that have succeeded in hitting the 2 red balls and selects the lowest speed level combination. In the end, it returns the best combination of the degree and speed level to the ball. Last but not least, ball position estimation with a web camera. To make this entertainment robot practically manufactured, we needed to use freeware which does not need to buy licenses. Python is one of them. Python is a script language and has a lot of libraries, including OpenCV. Now let's get to how the camera estimates the ball positions. First, it takes a wide picture of the pool table from certain height in 640 by 320 pixel size. We put a circle form of stickers on the four corners on the pool table to use them as an original picture basis. Because the camera cannot be perfectly looking at the distance from the corner to the center of the camera evenly, the picture needs to be flattened. To do that, we thought of calibrating the camera. However, the camera does not make any distortions. We use perspective transformation to make the taken picture of pool table image rectangular. You set the 4 points P1 through P4, and by using warping and perspective transformation in OpenCV, you can spread them into the form you want, like this output picture. This example shows the selected 4 points in original image transforms into a square image. And then next thing we did was to detect the center of mass of the balls. However, because of the disturbance such as brightness, shadows, and so on, it is not easy to recognize the ball positions. Here we had to think differently to solve this problem. So first, we made all the blue values in the image 0, since the surface of the pool table contains blue mostly, which made us hard for detecting the ball edges when grayscaled. And then we made gray image with red and green values. After applying canny edge operation, we blurred the image with 5 by 5 kernel to make the ball edges more clearer. And then another canny edge operation. Now we got more clearer ball edges. To fill the balls with white pixels, we applied 8 connectivity labeling algorithm. Now we need to number the balls. We just had to use labeling algorithm, and here we use it again, but with the equivalent table. Thanks to the equivalent table, we number the balls as you can see in this image, giving each ball a different intensity value. Now we can get the center of the mass position of the balls by tracking the gray image intensity. With the 4 ball center positions, we made the circle of 5 pixels of a radius to the center position of the balls, and mapped the area into the original image and extracted the BGR values to recognize the colors. In this way, we could get estimated ball positions. Because of unfortunate defects in motor drive, we could not finish combining all the parts together. However, still we are trying to finish the project, and we hope it's done by the end of this month. Thank you for watching. If you have any questions, please send email to here. Thank you again.